practice, the steady state assumption, how to develop the equations for the steady state assumption, and then go through the steps. And I'm not going to make you do all of the math to get there. Interestingly, Ryan pointed out a different way of approaching the math that was actually quite nice. So I'll actually bring that up as we do this method for the substrate inhibition. So one of the problems that can happen, particularly, so you can have a system where you have substrate and enzyme, and as you add more and more substrate, the enzyme can actually end up being inhibited by the substrate. So this is a problem particularly in things like wastewater treatment, where you've got a small, but your substrate is actually the waste. So you've got an enzyme that's trying to convert the waste, say a hormone in your wastewater that is not good for fish, and you have an enzyme that is trying to convert it into something that's not damaging to the environment, but you've got it there in relatively small quantities. You could see a circumstance where the substrate itself potentially starts that it is trying to be broken down by the enzyme, actually has the potential to slow down the activity of the enzyme as well. So, as I said, the place you see that most is wastewater. The general scheme for substrate inhibition is actually very similar to uncompetitive inhibition with an inhibitor, except instead of the inhibitor, you see substrate as being the inhibitor of the enzyme substrate complex. So we get PS into, we'll call this KS into KM. So if you want to consider it, you could do KS2 plus, like KS2, little KS2, KS minus 2 if you wanted. But essentially what it's saying is that you can have an enzyme that has more than one binding site, and when more than one binding site gets full, the enzyme becomes less active. So the substrate itself can be an inhibitor of the enzyme. So what I'm going to do is show you the rapid equilibrium approach. I'm not going to make you go through it because I think you're pretty comfortable with going through rapid equilibrium approaches. So here we've got KS1 is substrate, enzyme substrate over ES2. Enzyme substrate complex. Okay. The way that Brian solved it is really similar to what I described before, except instead of substituting in remember we put the enzyme balance before in terms of E, and then put that into, say, this one, and then came up with an expression that we then put into that one, or we put into that one, for example. The way he approached it was he put both of these ones into the enzyme balance. And it was much more straightforward to solve. So we've got the enzyme balance, E naught equals E plus ES plus ES2, right? So he did an expression here for E. So it was, say, E naught, correct me if I'm wrong, Ryan, E naught equaled, would have been ES KM prime over S. Is that what you did?
For E, yeah, it's just.
No, what are you solving that one for E?
No, you're going to solve that one for E. It gives you ES.
Yeah. trying to solve for ES, not for ES.
Yeah, so we're trying this plus, and then we put this in terms of ES2, so it
That's
was,
ES over KS1.
yes, S, ES over ES1, right?
Should be KS2.
KS2, yeah, yes. Did I put KS, this
The
is all
textbook
KS2.
uses KS1, you just wrote KS2, so.
I wrote KS2
Yeah.
here, so just for the sake of consistency, we'll pick one. It doesn't really matter what, make sure you pick as long as you're consistent.
Oh, that's one rather than two.
It doesn't matter, you can,
Sure.
I was mine, like substrate inhibition.
yeah, I wrote it as a 1, but let's call it 2 just for the sake of consistency, because I wrote 2 over here. I think the textbook uses 1 throughout. It doesn't really matter, we're just using the same thing. Okay, so as you can see, that one's considerably easier to factor out the ES, doing it that way. So thank you, Ryan. Now what you come up with when you do that is you have rate equals Vmax. Remember Vmax is K2 times E naught times S over K M prime plus S plus S squared over K S. Okay, and if you do the factoring, actually the math to get from here to here is pretty straightforward. You end up with a similar expression the other way, which you then can rearrange with a little bit of extra work to come up with the Vmax apparent, Kmax apparent approach that we saw before. But it's a much more straightforward way to do it. Now, I'm going to take you one step further through this and just say, if we take the inverse of both sides, we get now, the reason I did that is because I want you to think about what happens if we have low substrate concentrations or high substrate concentrations. So if we have high substrate, really high substrate concentrations, that's going to be really high. That'll be unaffected, but that'll go to 0 at really high substrate concentrations. Okay, so if you have a high substrate concentration, then you end up having 1 over V equals 1 over Vm plus S over Ks2Vm. So basically, at really high substrate concentrations, what you're seeing is the rate is inversely proportional to the substrate concentration. So as the substrate concentration goes up, the rate goes down at really high substrate concentrations. Right? Does that make sense? Generally? Just conceptually? So let me say that again. When you have really high substrate concentrations, this whole term will go to 0. So what you're left with is 1 over rate is proportional to substrate concentration. Or conversely, rate is proportional to 1 over substrate concentration. So as your substrate concentration goes up at really high substrate concentrations, your rate goes down.
Makes sense, because the whole thing of the substrate is blocking the around.
Exactly. Exactly. So conceptually, just from the mechanism, you have lots of it, you end up with lots more going into this other enzyme substrate complex. Is the idea. And not working as well. Conversely, if you have very low substrate concentrations, so low S, that one goes to 0. That term goes to 0. And what we end up with there, if this term is 0, This is just your Lineweaver-Burk plot. That is your Michaelis-Menten kinetics. So at really low substrate concentrations, this disappears and you're back to straight Michaelis-Menten kinetics. Make sense? So as your substrate concentration increases at low values, your rate is going to increase. Right?
So with the enzyme, what would it look like if there's like two active sites?
Yeah, so it's sort of like there are two active sites. Or if you were, here we've said it's sort of similar to the enzyme substrate uncompetitive inhibition. So you could similarly think that the substrate may come and bind to the enzyme substrate complex. So two substrates might bind to the one site and make it not work as well. So maybe they can both fill the active site and then it can't make product because it's not the normal reaction. So there are a number of ways that it can happen, in like conformationally that it can happen, but it does happen not infrequently that you have way more substrate and then it's problematic. So what that ends up looking like is, here's our substrate concentration, here's our rate, there's our normal Michaelis-Menten kinetics. So at the start, you have normal Michaelis-Menten kinetics with the very low substrate concentrations. At the end, when you have really high substrate concentrations, it starts going back down. Okay? And then you have some kind of maximum that happens. Okay. How would you figure out what the ideal substrate concentration is, the optimum substrate concentration? Yep, so, well, the derivative d v by ds, because it's not time, right? So the derivative of that with respect to s is 0. So that's usually how you figure out a maximum. You look at the rate, and as soon as the rate flatlines, that's your maximum or minimum. Right, so you can actually go and look at this equation and do the math, which I'm not going to make you do. And what you end up coming up with is S max equals and then if we draw this in a Lineweaver-Burk plot, where that's your normal new inhibition. What are we gonna, any idea what it's gonna look like? So look back at this one and figure out what it might look like. So low substrate concentrations. So that's out here. What's it
Looks
gonna look
like the normal one, right?
Yeah, so out here it's sort of like that. But then at high substrate concentrations, what happens to our rate? The rate decreases, so 1 over the rate increases dramatically. So you end up with something like that on your Lineweaver-Burk plot. So if you get 3 points, say, and they're clearly not linear on a Lineweaver-Burk plot and they're doing something like this, you might guess that what you're seeing is substrate inhibition. Okay, now does everyone follow how we did this for rapid equilibrium? Yeah.
Or getting to the last step there, from when we solved Ryan's equation for ES, what was the V equals something ES? What was that something?
So V equals,
It was K2 ES, okay.
yeah, so same, because we've got this, and we're saying this reaction scheme is, again,
Oh,
as
right, that's the
normal, only
important one.
going in one
Okay.
direction here. That gives us our normal rate. able to, if you had 5 data points, would you be able to find intercepts that satisfy your normal inhibition type equations or your normal Michaelis-Menten? Absolutely not, because there are no intercepts in this case.
So you could also try, so like, if you didn't have a plot, you could try solving them out and you can't find an intercept. Is this the only untitled inhibition we're doing?
Well, we're going to cover inhibitions that are caused by environmental factors, but they are a little, they're not like this. So we'll cover that in a little bit. But first, I want you to give the steady state a try.
Is it also always going to be positive, or can it cross the x-axis?
In substrate inhibition?
I guess not, right?
Yeah, even in a Lineweaver-Burk plot, you're actually projecting so that it crosses the x-axis. It never actually, exactly, you'll never actually cross the, like your data points will never cross the x-axis. It's just that you've got a linear thing that if you project it, project your line beyond the experimental points, then handily your intercepts give you your key parameters that you're interested in to model the situation. So good question. This should really be dotted because it's not real. Definitely no negative concentrations. Yeah. Any other questions before we start trying the steady state approach? Okay, so steady state approach, I just want to remind you, what you're doing is saying that the change in concentration with time of ES is going to be 0. So everything that feeds into it equals everything that feeds out of it. Of ES. Again, you're not looking at the equilibriums, you're looking at the actual species. And similarly, ES2 is going to be, the change in ES2 with time is going to be 0. So that one's a bit easier to figure out. You have one thing that's feeding into and out of it. So all I'm going to ask you to do is set up the equations for steady state. You don't have to solve them. If you want to, you can solve them. I actually haven't solved them myself. It would be interesting to see if you can get to the same solutions. I think you should be able to, but we'll see. If you want to, you can. But all I want to see is that you can set up the 2 steady state assumption equations.
This is what we did this morning, but for steady state.
Yeah, exactly. So it's the same as you did this morning, but you now have a steady state assumption instead of a rapid equilibrium assumption. No, we're doing it for the substrate inhibited one. So this one term goes to 0 if you have really high substrate because it goes to 2, and then that whole term goes to 0. Substrate goes to 0. Oh, so the consequence of so for example there. As you increase substrate, your rate increases. Yeah, which is what you said. And then it really grows with concentrations. You're back to the normal Michaelis-Menten where if you increase the amount of substrate, you increase the amount of rate. Yeah. Yeah, so well, yeah, so this is only at my substrate. If you increase further, then your rate will decrease. So if S at my substrate, if S goes up, your rate goes down. If S goes up, your rate goes up. And vice versa. So if your S goes down, you're going to increase your rate. Yeah.
What?
What's your D what my D1 equals what?
So, I guess this is
see is that with time it's.
Did you get it like before the big bases?
So there should be
Right now it's
1, 2, 3, 4, 5 terms.
Oh, yeah, so this is, oh.
That's like the, like.
So I was just,
When do you get this?
Yeah, we can.
you need this.
Okay, sure.
Said he paid like 3 extra bucks.
Sure, you could do that, and 5 terms.
Got it.
Yeah,
Yeah, I
yeah,
paid, I paid standard. But you still.
Is that, yeah, I don't know.
yeah.
Gabe did
For
like
those
express
zero.
shipping, it was like $3 extra. I got it a lot
Oh,
easier.
yeah. Cause like I feel like, cause like we still have to do things for the merger, so I feel like we still have to.
Yeah, I mean, it was standard. But like it didn't matter, like,
Yours, it didn't come to the date it just said.
no, it was early, but I did standard shipping and apparently the item was too heavy, so I paid the extra $5, right? Yeah, so Gabe, not anywhere.
Well, it's around every.
Oh, I forgot that. So you're trying to.
Oh, yeah.
Yes.
It's the same assumption we talked about all the classes ago. Oh, yeah. So the steady state assumption is saying that the change in any of your complexes with time is irrelevant. So the change, let's start with the ES2 complex. So it's easiest. Actually, the change in that with time equals how fast it's made minus how fast it's lost. So how fast is it measured? Okay. We can call it little k S2, little k minus S2, for example. So how fast is it?
Like ES2 is made, like ES2 is made, by multiplying KS, sorry.
Little ks2,
KS2,
which is the down, yeah, times. I think so. Yeah.
What would you call it?
You could call it ks minus 2.
Oh, sorry. I wish that was out here.
Okay, so just if anyone's, because I put equilibrium stuff in here. You could equally call this.
Yeah.
Anyways, what I was saying is Gabe didn't have to pay that $5 thing, so he got earlier shipping.
And get it paid.
Oh, I just paid $5. I saw you were doing this like 2 weeks ago. Seriously.
No.
Yeah,
I
I saw
started
you
doing it,
last
like,
week.
yeah, but then I didn't do it.
So who's
Because of this.
Yeah.
I'm like, I'll do it when I get home.
That's all the video.
It's a proper.
No, cause like.
Similarly, just like how you want the minus 1.
What order? Yeah. You didn't have to pay that extra $5 or something.
I would suggest trying,
You have to pay that extra $5.
You did it? But it's still like, cause it said.
Basically, the $5 in expression. Yeah.
Yeah, so I got it sooner than everybody else. Yeah. So it's good.
It's real.
Yeah.
So it's.
Oh, no, it's just like.
Oh, yeah.
I thought we were doing the one that wants me there today.
If you want to go further, you could try the method where you sub into the enzyme balance. But I think we're good. I just want to go through and make sure that everything's on the same page. So you got it? And then you got to do the TCS2 one as well. So all of it changes.
Yeah, it's just equal to each other. Yeah.
What did he
No,
say?
it's just like this equals to.
Yep. Yep. Yeah. Did he?
Or changing is too. Oh, so basically, that's why it was Thursday. Yeah, but that's why I put it for Friday because I wanted to do it for
Basically, you're doing great. Line where yes, change your yes with time to 0. And so once you brought this up, we haven't learned the circles yet. I did one or two. Oh, is that? Yeah.
I know, but I still, I panicked.
Oh, yes, it's mixed. Oh, that's what that's.
Because like this is positive situation over a negative reaction.
Reinformation, this minus
Like not. So
Oh, it's like the very first day.
will be done.
I like getting things down.
Yeah.
Yeah, no, we need that. Probably did once. Do you go to the Yeah, I did go for it, yeah.
I never know what's so
But I don't want to wait until Wednesday morning. Let's do it. So I would say.
That requires going. Figuring out their situation. Yes, they have to.
That's happening. It's not water. This is what I'm going to be doing all night today.
This reaction.
Now what you're able to do is.
Yeah.
I'm glad
This is part of this reaction.
Substrate and
I mean, how like 1 hour.
Yeah, except it's 3 seconds.
I'm like, that's a lot. And it's a junior class. But like,
substrate.
But I never knew.
Simon and the lab Wednesday.
Okay, I think everyone's got this. Did anyone go the extra step to see if you plug it in, if you get the same thing?
If you change the constants around a little bit, otherwise it's the same.
I think you end up with creating a KM that is a slightly different.
KM is just the the KS2 is just what the numerator is. It'd be a different KS2.
Okay. Okay. So like the same basic structure by doing it that way.
No, I agree.
What do you do after this?
Okay, so I'm just going to review all the different enzyme inhibition methods that we've talked about so far. So this is what your substrate inhibition looks like. Okay. And then these are all Lineweaver-Burk plots, so all 1 over rate versus 1 over substrate. And this is your normal one. Draw that a few times. And that's your no inhibitions. Okay, so anyone remember competitive? Maybe I'll just remind you what the intercepts are. 1 over V max and minus 1 over Km are your normal intercepts. Yes, prime, because the equations that we're using were derived from rapid equilibrium. So again, anytime you've done the derivations based on rapid equilibrium and use the Km prime, you can use just straight Km when you've done the steady state assumption. Okay, so competitive inhibition. Anyone remember what that should look like compared to no inhibition? So this is where we've got an inhibitor that can take the place of the substrate in the active site. But if you have lots and lots and lots of substrate, it'll displace all of the inhibitor. So which constants will be the same in that case? The 1 over Vm, exactly. So that one stays the same. Okay, so competitive inhibition, you get to the same maximum possible amount. And then, do you remember whether the Km goes up or down in that case? Closer. So, actually then the minus 1 over Km goes down. What does that mean that Km is doing? It's actually going up. So remember the higher Km means that you basically have less affinity to the of the enzyme and the substrate to one another. Okay. So then we've got non-competitive. So remember, in non-competitive, you've got the inhibitor going to a different site on the enzyme that makes the active site have less affinity for the enzyme or for the substrate. So it just doesn't hold on to the substrate as well. It doesn't react. It doesn't allow the substrate to react as well, I should say. When the inhibitor is there, it doesn't matter how much substrate you add. The inhibitor will always inhibit the enzyme because it's at a different active site. It's affecting it at a different site from the active site. So for the non-competitive, what stays the same and what changes? Or does anything stay the same? What happens to Emax? Anything in the non-competitive? So this is the one, this is non-competitive, so we've got our enzyme here, we've got our substrate here, we've got our inhibitor over here. That means that that can't go to product as easily. It just doesn't react as well with
So it's independent of substrate concentration.
It's independent of the amount of inhibition is independent of substrate concentration. Just depends on the inhibitor concentration. So are we gonna get to, can we ever get to the same maximum rate in that case? Right, so you actually have a lower maximum rate in this case when it's inhibited, but typically you actually end up with the same Km in the inhibited case.
Is this the whatever VM applied, or apparent rather?
Yeah, so this will be our 1 over VM apparent. That is our 1 over Km apparent. In those cases. And then
So it's not related to substrate concentration.
right. The amount, you can, in this case, you have, I mean, your rate is going to be related to substrate concentration, but the presence of the inhibitor changes how the rate is related to substrate concentration. Right, so basically imagine, what the inhibitor has done has changed the enzyme from being a very active enzyme to not a very active enzyme. So still, if you add more substrate out to the limit, then it'll have a higher rate. But eventually it's all going to get filled up and it'll reach its Vmax, and then the Vmax that it can reach is lower than if there's no inhibitor there. Everyone's comfy with that? Okay. And then the uncompetitive, we actually had both change and we established at 130 that it's not necessarily a parallel line, but you have changes both in Vmax apparent and in Km apparent when you have uncompetitive inhibition. And again, uncompetitive inhibition, the inhibitor binds to the enzyme substrate complex together. Okay. So the reason I'm highlighting that again is because this is where these kind of plots are where you start pulling experimental data and figuring out, you can compare a normal reaction at 2 points. I could give you 2 experimental points there, and you could figure out what the Vmax and the Km are easily from those 2 experimental points, and then I could give you 2 experimental points that are inhibited, and you could figure out what your new VM or Vmax apparent and what your new Km apparent are. So then I could ask you what kind of inhibition is this likely to be, and if you're really close on Km apparent equaling or really closely equaling or Km non-inhibited, but your Vmaxes are different, then you can say, well, this is probably non-competitive inhibition, and so on with the other ones. Okay, so I could easily give you 4 data points, say what kind of inhibition is this likely to be. If I gave you 6 data points, I could even ask you what K2 is, because Vm equals K2 E naught. So I could similarly ask you what K2 was, or sorry, if I gave you 2 enzyme concentrations, I could ask you what K2 was. If I gave you 2 inhibitor concentrations, I could ask you to back out what K inhibitor is, which is a little bit more complicated because you have to pull it out from you'd end up with 2 different, say, VM apparents, and those have their equations that you came up with before. Make sense? Awesome. Okay, so the other thing I'm going to do next class is I'm going to show you how some of this is useful when you have immobilized enzyme systems, and what you can actually do with some of these equations in immobilized enzyme systems when you have CSTRs. What we're doing sort of subsequent to that is doing some of the modeling of diffusion limited transport versus reaction rate limited reaction rates. So we're gonna start looking overall where we're going with it in the next week or so. But before we do that, we're going to use up the rest of the class talking about what happens with pH and what happens with temperature. So I'm not going to take super long with that. The concepts are very similar to what we've seen before. So when we talk about pH, generally what would you think would happen with pH? So where are most enzymes, say in the body, most active? Around what pH? Yeah, 6 to 7, depending on where it is. You know, there are some enzymes that act in the stomach. Those enzymes are most active around pH of 2 or 3, because you have lots of acid in your stomach, and those enzymes break down your food. But the enzymes that are in your cells, around the surface of your cells, around pH 7. So it all depends where the enzymes generally are most active. But in those cases, what you see is what might you expect if you change the proton concentration either up or down, your pH up or down from the concentration that it's usually at? What would you expect to happen to enzyme activity? So you'd expect it to have a maximum, right? Part of that is because the way that enzymes interact with their substrates is largely based on electrostatic interactions. So if you're changing how protonated all of the side groups are on your active site and how protonated your substrate is, suddenly if they have a lot more positive ions, they're not going to attract one another very well. Or if they both have more negative groups on their surface, again, they'll start to repel each other. Right? So the way you model that is you say, well, we're going to say actually our optimum enzyme is going to have one hydrogen group on it, one proton on it. And that one then interacts with substrate, form an enzyme hydrogen substrate complex that K2 has our protonated enzyme plus your product. So here, if you add more protons, okay, you're going to come up with something with an extra proton on it, or you can lose a proton and end up with something that's missing its normal proton. Okay, does that make sense more or less? So this is how changing the pH quantity actually can affect what's going on. Okay, and we're going to call it K1 here and K2
So
here.
K1 is for more acidic, K2 is for more basic.
Yeah. Yeah. So doing the rapid equilibrium analysis, we can do our normal definitions. Km prime. Here we're going to say it's our protonated enzyme times our substrate divided by our enzyme protonated substrate complex. K1 is K2 Okay. Makes sense so far? Everyone's
But then we have two K2s, like I know one's larger, like a large K, and one's just the reaction thing, but it might get confusing.
Oh, I see what you're saying.
I'm just changing the little one to KP.
You can change so this is also often called KCAT in the biological literature, so if you're more comfortable calling that something other than little K2, you can call it KCAT. So that you don't get confused on your forward end versus. Now the enzyme balance is a little more complicated.
fake K1 there, fake K2?
These are fake. Those are your equilibrium. And for this purpose in this one only, I'll call it KCAT as our little K2. So if you do the math, what you come out with is rate equals Max S over So here we've got a CAM apparent that's very influenced by how many protons you have. So if you add a bunch of protons, it changes it. If you subtract a bunch of protons, it changes it. So this is very much like what we saw with the substrate, where if you have a lot more, it'll change it. If you have a lot less, it'll change it, and you end up with a maximum.
So what would you be solving? So now we have 3 equations, we have 2 equilibriums, right? So what would you be solving the enzyme balance equation for? For EHS, it looks like?
Yes. So
EHS.
so same thing. You could do the strategy I really like that Ryan did with your equations. You could get an expression for EH.
No, EHS, right? So
Well, what you're trying to end up with is an expression for EHS.
yeah.
So into here, you could use this one to put in an expression for EH. And there, this one you could use to put in an expression. So sorry, this one you could use to put in an expression for EH2, and so on. Okay. Everyone's, that more or less makes sense. So just to finish off the class, the consequences, just as before with the substrate, you've got this, you've got pH, and you've got a maximum percent max activity. Okay, and if you do your optimization so that as pH changes, or as your basically your DH plus by pH is 0, then you get H plus concentration. Optimum equals root K1, K2, or pH. Optimum equals 1/2 pK1 plus pK2. So that's log K1 or log K2. So basically you've got how fast it gets inactivated as it goes up in pH, and how fast it gets inactivated as it goes down in pH from the optimum. So your K1 and K2 will tell you, do you lose activity really quickly by going up in pH past the optimum, or do you lose activity really slowly by going down in pH past the optimum, or vice versa? Okay, so this is very, very much, mathematically, very, very much like the substrate inhibition concept. You've got this maximum that gives you your optimum optimum pH at which the enzyme operates best. But some enzymes have quite wide areas where you're above 90% activity, and some are very, very narrow and very specific for a given pH, depending on what those K1s and K2s are. Did I forget my negative?
Yeah.
Oops. Oh, sorry, it's negative. Yeah, negative log P1. Absolutely. Thank you. Just like pH. Yeah. Yeah. Yes, thank you for noticing that. next class, we'll talk about the effect of temperature on